Okay, so in this video we're going to talk about what it means to solve a linear quadratic system. So first up, I just want to talk about what a system means. So system is basically when we've got more than one equation. So a system of equations is when we have at least two or more equations that are considered together. So two equations that we're looking at the same time. Now, if we were to graph these, the solution to the system of equations are basically the points of intersection. So for us, one of our equations is going to be a straight line and the other is going to be a parabola. And there are three different options. And again, solutions, that's just meaning points of intersection. So our solutions are points that are both on the line and also the parabola. So one option is that we have no solutions. And in this option, the line is lying underneath the parabola, and our quadratic function is never going to be crossing the line. So it's always going to be above. The quadratic function is increasing faster. So this is going to go really, really steep and it's never going to hit. So that's one option, that we get no solutions. A second option is that we get one solution, 1 point. This one is showing it as the vertex, but that's not always necessarily the case. But basically what's happening is that our line and our parabola are meeting at 1 point exactly. And then the most number of solutions we're going to have here is just 2. So at most there can be 2 distinct points where the line and the parabola are intersecting. So for us to be able to solve these, there are a couple of different methods. You can solve graphically, even though it's not always super exact. For us, we're going to be doing algebraically, so we're using substitution. So if both of our equations are given as y equals, so we've got maybe y equals mx plus b and y equals a parabola in vertex form, we can set the two equations equal to another. So as an example, let's say you've got y equals x squared is your parabola and your line is maybe 2x minus 1. We're looking for the points with the same y value, so we're going to sub this part equal this part. So we're trying to solve x squared equals 2x minus 1. Okay. And really, there are two parts to this. We're going to make equal, solve for all x's. There could be 0, 1, 2, 0, 1, or 2 x's. And then because we're looking for the points, we need to find y for each x. Right? Because the x gives us where it's happening, but it doesn't actually tell us the point. So let's say here, if you found that x was 1, you could sub into either the line or the parabola to be able to find your y. And then same thing if x was -1, sub into either equation. Usually the line's going to be a little bit easier to sub into, but it's really up to you. And as a note, I just squished it on here. Please try these questions, and I'll post those on Moodle as well. So let's just dive in, try a couple of examples, and we'll get a feeling for what's required here. So solve each system of equations, and we're going to include a sketch just to kind of visualize what's actually happening. So the first thing we want to do is just set these two equations equal to each other. Okay, so we're trying to solve for x, and we do that by writing these two equations equal to each other. We want to know, when does this parabola equal this line? When are they equal? Now for us to be able to solve any quadratic equation, I showed that in the last video actually, we need to expand everything out, bring everything over. We're trying to get it so that it equals 0. I think first I'm going to work with the x plus 1 squared and work on expanding that. And remember, for these, x plus 1 squared, we need to write twice. It's not just x squared plus 1 squared. So I'm just writing it twice. And then from here, you can choose to distribute the negative to this bracket. Maybe you want to FOIL first and then go negative. I'm going to go negative x minus 1. I'm going to go this way. If you want to start bringing everything over, you can. For me, I just like to expand first. So negative x squared, we get minus x minus 1 plus 4, and keep going. Let me just collect like terms. And you can choose to bring to either side. Because x is negative, I'm going to bring everything to my right side. So when this comes over, it's positive. When this guy comes over, negative 2x plus 2x is gone. And then when this comes over to minus 3, we get minus 1. So this one's simplified very nice. From here, we either want to factor or we can use quadratic formula. You could bring your 1 over, but let me just do this one by factoring just so we get into the habit. And once it's factored, we want this to be 0, so either the first bracket is 0, which makes x negative 1, or our second bracket is 0, which makes x positive 1. So that's really only step 1. We set our equations equal to each other and we solve for the x values that would make this true. But once we've got these x's, we do need to find the 2 points. So let me go point 1, our first point. We can choose to sub x into any of the equations. Let me sub x equal negative 1, and I think my line is nice. So let me sub this into negative 2x plus 2. So y equals negative 2 times negative 1 plus 2. So y is 2 plus 2, or y equals 4. So one of our points of intersection is negative 1 and 4. And we'll do the same for our second point. We sub the other x values, so positive 1, and we can sub it into the same line, or you can sub it into the parabola if you choose. But it's giving us a different point, but still both on that line. Set this up a little bit more. So y equals negative 2 times positive 1 plus 2. We get 0 for this one. So our second point is 1 and 0. So at the end of this, please just give me a therefore, the points of intersection or the solutions. If there's just one, you can say that. Maybe it happens to be no POIs, but it's, please do just give me a therefore. Okay, so we've solved for our 2 points. We know the 2 points where these two graphs are going to meet. Now let's actually show what it looks like graphically. So our two functions again were y equals negative x plus 1 squared plus 4 and y equals negative 2x plus 2. I'm not going to ask you to graph it and check on a test or anything, but it's nice to be able to do. So let's start with our parabola is probably easier. This negative means it's opening down, and we can tell that our vertex is going to be negative 1 and positive 4. So negative 1 and positive 4. Now because this hasn't undergone a stretch or compression or anything, it's still going to have the normal step pattern. So our points are going to be 1 away, then 3 away, and so on. And if you haven't learned step pattern, that's no problem. Just know that the vertex is at negative 1, 4, and it's opening down. Just the general shape of this is fine. So this is our parabola. Now for our lines are actually pretty easy to graph too, but it's probably been a while. This negative 2 tells us our slope. So what this means is that for every 2 points we go down, we move 1 to the right. And we start this at a y value of 2. So this is our y-intercept. So starting at 2, we go down 2 over 1, down 2 over 1. We can keep repeating. And if we go backwards, we would go 1 and 2, 1 and 2. And we try and connect these as straight as possible. And we can see the 2 points that we solve for. Negative 1, 4, it's crossing right at the vertex, and 1, 0, it's crossing at one of the roots. So that's what a full question for one of these would look like, where we actually have 2 solutions, 2 points of intersection, and we've been able to solve for both of them. And then we've just kind of verified using the graph that our points were actually accurate. I want to try a couple more examples. So these may or may not have solutions. We won't know until we try them. One thing to point out about the other one is that it kind of started in this form where y was already isolated, whereas this one we need to bring over the 2 first. We need these to be totally isolated for y. So my first step in this one, kind of a preliminary step, this 2 needs to come over so that y is on its own. And now from here I can make my 2 equations equal to each other. So x plus 3 squared minus 2 is equal to 3x minus 1. And again, unfortunately, we do have to expand out this bracket. X plus 3, x plus 3. And I think while we're here, might as well just start bringing things over. Get a little bit more done in one step. Then we can FOIL this, x squared plus 3x plus 3x plus 9, minus 2 minus 3x plus 1. All right, and then let's look for our like terms. X squared, I've got 3x. 9 minus 2 is giving me 7, plus 1 is 8. Okay, now this one doesn't look as nice. It's definitely not factorable. We don't have anything that multiplies to 8 but somehow adds to 3. So if you do run into this scenario, you do need to try and check for solutions using the quadratic formula, unfortunately. Just because it's not factorable doesn't mean it doesn't have solutions. So we've got our a equals 1, b is 3, and c is 8. You could use the discriminant to check how many solutions you have. That's one option. But might as well go right into our quadratic formula just to see. So we've got negative b plus or minus the root of b squared, so 3 squared minus 4 times a times c, and then over 2a. And if you're looking at it, you can probably tell 9 minus 32 is going to give us a negative number. And because we can't square root, we actually have no solutions in this case. So no solutions. There's no x, we're not going to be able to get an x value from here, not a real one at least, which means there are going to be no points of intersection. Okay, so let's check what these graphs are going to look like just to make sure we didn't actually screw something up somewhere along the way. So our vertex here is going to be at negative 3, negative 2. So negative 3, negative 2. And again, there's no stretch or compression or anything. It's just going to be opening up. So we're imagining that this is our origin. We've got 1, 1, 2, 4, 3, 9 if we wanted. But our parabola is looking something like this. Okay, and let's try our line. We've got a y-intercept of negative 1 and a slope or a steepness of 3. So it's starting on our y-axis at negative 1. And for every 3 squares we go up, we go right 1. 1, 2, 3, 1. If we want to backtrack a bit, we can add in a few more points. But I think our algebraic solution makes sense. This line is going to be going up at a steady pace, but our parabola is going to be increasing more and more quickly. So yeah, the no solutions makes a lot of sense for what we got graphically. Great. Okay, let's try one more. Let's see if this one turns out any differently. We want to start it off the same way again. You're always just making the 2 equations equal to each other. So negative 2x squared plus 3 is equal to 2x minus 1. And we can choose to bring this to whichever side we want as long as we're making it 0. So for this one, I'm going to send everything over to the right. You could do whichever. I just prefer to have my leading coefficient be positive. So if I bring everything over, 2x squared comes over. The 2x is already here. And then I've got negative 1 minus 3. Okay, well, let's see what we can common factor here. We can common factor out a 2. 1x. And we're kind of scratching our heads. What multiplies to -2 and adds to 1? Well, that works. Positive 2 and -1. Positive 2 and -1. Now, we're in the nice case of our trinomials. There's nothing in front of the x squared. So we can just go x plus 2, x minus 1. Because this should still factor out the same. X squared plus 2x minus 1x works, and then minus 2. And then our 2 that we common factored out at the beginning is just going to stay at the beginning where it was. So we got lucky. This one is solvable. And again, we're going to get 2 factors, or 2 solutions. So if x plus 2 is 0, x equals -2. And if x minus 1 is 0, x equals positive 1. And remember, for these, once we've got your x's, we're not done. We still need to find the points. So our first point, we can sub x equals -2. And you can choose either equation again, but I'm going to choose my linear equation, and I'm just going to call it 1. So y equals 2x, so 2 times -2, subtract 1. So -4 minus 1, or y equals -5. So this is the point -2 and -5. And then our second point, we're going to repeat the other way, or repeat using the other x value. So we can sub x equals 1 in the same equation if we want. So y equals 2 times 1, subtract 1. So 2 minus 1, y equals 1. And this point is 1 and 1. So we have 2 solutions, and let's just do a nice little check again, make sure it actually works out pretty nice. So our vertex for this one is going to be 0 and 3. It hasn't moved at all. So our vertex is 0 and 3. And this one, it's opening down because the negative, and the 2 means it's been stretched vertically by a factor of 2. So all of our usual step patterns have doubled. So hopefully our graph looks something like this. All right, let's graph our line. We're starting at a y value of -1, and our slope of 2 means for every 2 it goes up, over 1. And if we were to go backwards, yeah, this looks awesome. So just connecting these guys, and our line is 2x minus 1. Not the straightest line, but it's showing the points, which is exactly what we want. And again, this would just be to verify. I wouldn't be asking you to graph it on a test or anything. The main points here is just make sure that your equations are already isolated for y. You're setting them equal to each other. Expand if you need to. So in the last one, we needed to be able to expand out the 2 brackets before we could start solving. And then once you have it equals 0, solve either by factoring, try a quadratic formula if you need to, but try solving however you can. And then for each x that you have, you do need to sub it back into one of your equations, because our final answer, which I forgot here, is saying what your solutions or the points of intersection are. So -2, -5, and 1, 1. So hopefully that looks good. If you have any questions, feel free to ask, but that's solving systems of equations.